Good day, I'm Dr. T and welcome to my dining room table. So today I'd like to talk about aromatic compounds, naming them, and just in general talking about them. So aromatic compounds are fairly important because if you recall, they are going to have a structure that has a ring that has alternating double bonds. So I will have a ring, it's going to be a hexagon, and hexagons are one thing that as chemists we get to draw a lot of. And it has this alternating double bond pattern. Now, they are in resonance. So that means that and this are actually the same molecule. Those double bonds can exist in both locations. So for that reason, we are going to draw them in their hybridized form, which is a circle in the middle. Okay, and that's what I've done over here. Sorry for wiggling the camera. Okay, so with this guy, because of this hybridization, we get what's called a pi system. The electrons in the double bonds, so the 6 electrons, 3 double bonds times 2, are shared communally between all 6 carbons. This is the characteristic of the aromaticity, is creating this pi system. It's called a pi system because the second bond is a pi bond, and that's what's being shared. Okay, so we need to distinguish these from a non-aromatic system. So we will call a ring that has the sharing of the pi bonds a benzene ring. Now, that's if it's going to be the root. If it's the core of our molecule's name, we'll call it benzene. If it's not, if it's a branch, we'll call it a phenyl group. And we'll get here shortly to this guy over here. You'll notice the pronunciation is going to be a little bit difficult to distinguish. But written is pretty straightforward. Okay, so with these guys, if I was to say stick a chlorine on my benzene, then I would have, a molecule like this. And I would call it chlorobenzene. Fairly straightforward. It's a ring. Wherever you put the chlorine is going to be the one carbon. You're good to go. If I put 2 of them on there, more than likely I would simply, call it standard UPAC approach. One comma 2 di. I forgot my di to start with. Dichloro. Benzene. Okay, fairly straightforward. Now, for historical reasons and because the electronic environment does drastically change some functional groups, certain functional groups when attached to a benzene ring actually change the whole name of the root. So if I put an alcohol on there, this now becomes a phenol. This is actually one where we can really see the effect of the electrons fairly clearly. An alcohol won't lose its proton unless it's under extremely alkaline conditions, conditions that are beyond what can be achieved in an aqueous environment. However, by adding the electrons over here, these electrons interact with the oxygen and make that hydrogen much easier to come off. And so this will become deprotonated, forming an anion at pHs that are definitely obtainable in aqueous environments, kind of a moderately high alkalinity. Not nearly as much base is needed than would be otherwise needed if it was not on an aromatic ring. So this guy's going to be a phenol. As I alluded to earlier, phenol and phenol are very close in terminology, and they're completely different things. If it's a CH3 group, this is a little bit more for historical reasons. If this is a CH3 group, then it's called toluene. And if it's an amine, so an NH3, then it's called aniline. There's other distinguishings. I'm not really going to go into that. Now, a few other weird names, and these are a little bit more kind of for the historical reasons. You can name these kind of more classically UPAC, but you will see them quite often used for the historical naming. If I have 2 CH3 groups, then that's called xylene. Now, you'll notice how I did this really weird thing where I had this CH3 bond into the middle of the ring. And what that is doing, when I send my bond not to a carbon, but to the center of the ring, I am being intentionally vague as to which carbon that's on. Turns out there's actually 3 different types of xylene. So I could have, and I'm representing all three with this molecule by being vague, I could have this guy. And by the way, I'm putting one of the functional groups in the up position just for my convenience. These guys are molecules. They can tumble and spin all they want. So I could have this guy, and this is what we would call ortho or just O xylene. When looking at aromatic rings, the 2 and 6 positions are called ortho. They have very similar chemistry. They're ones adjacent to the thing you're discussing. Now, if I have this not in the 2 position, but the 3 position, then this would be xylene. And lastly, let's see if I ran out of room yet. If the CH3s are opposite to each other, then this would be paraxylene. Okay, fairly straightforward. I can use the orthometapara really with any functional group if I wanted to. So I had a phenol, let's say I had a chlorine off on, say, this particular carbon, then I would call that metachlorophenol. So fairly straightforward. Now, one last group of hydrocarbons I'd like to talk about are the polycyclic aromatic hydrocarbons. I know, long name. So in this case, I have naphthalene. This is the old mothballs. You're going to have 2 aromatic rings, and the important part is their pi systems are joined together. So, you can imagine there's a double bond there. Well, that one's part of this ring and that ring, and so they're going to be joined into one pi system. This gives them some rather interesting properties. For starters, this is flatter than a flitter. All of these guys are flat because of those double bonds. And this one continues on being flat. You could add more and more rings to it, make something that looks like chicken wire, and that is what graphene is. Graphene is this nice flat plane of polycyclic aromatic rings. If you get lots of graphenes kind of jumbled up, that's graphite. Which, once again, it looks like chicken wire. It seriously does. So yeah, there's a little bit of our aromatic compounds. Once again, the chemistry of these guys is greatly affected by that pi system. I can have, a chemical reaction taking place on one part, even over here, and it can affect all the way through it because it affects those electrons. So with that said, have a wonderful day, and I'll see you in later videos.